Hi guys, welcome to our channel of Sciences and Mathematics. Today we're going to look at a specific concept in chemistry, and that is the concept of aromaticity. Now that we have mentioned shallowly on some of our videos about the concept of some organic compounds being aromatic and others being not aromatic, we're going to look at the conditions which are required basically for an organic compound to be referred as aromatic, and some of the rules which they should conform with in order for them to be regarded as organic compounds. So without further ado, thank you and welcome. So I've mentioned that our topic for discussion for today is the concept of aromaticity. And aromaticity is a derivative of the word aromatic, or maybe aromatic compounds, as we have been talking or maybe mentioned in some of our videos that we have discussed about organic compounds. Now, the concept of aromaticity is is of course a property that is associated with the extra stability of certain types of pi systems. And of course, I had given a demonstration for the benzene ring to represent organic compounds, or maybe benzene ring to represent organic compounds or compounds of a similar ring systems. And now today we are going to look at how this basic property of aromaticity can be ascertained. So in that case, I've talked about these types of pi systems in some of our videos, and this is due to the nature of the molecular orbitals, and we talked about the pi and sigma bonds, and of the molecular orbitals when we were trying to illustrate the difference between the two bonds. So in one of our videos. Now, this concept of aromaticity is not restricted to substituted. It says that some of the substituted benzenes like chloromethyl, benzene etc., the common names or special names that we had given for toluenes, compounds like toluenes, because this is a metal substituted benzene, so this is a toluene, aniline, etc. Can be di, tri, poly substituted benzenes. So this property of benzene or the aromaticity is not restricted to substituted benzenes. Or substituted compounds. It's not also restricted to some of the compounds that we mentioned about, or the 6 member rings that have been basically using as aromatic compounds, or the representation of aromatic compounds, or just hydrocarbons. We're going to see that some of course, the carbon ions and the carbocations can be able to attain this special property associated with the extra stability that we are calling the concept of aromaticity. Now, this one is basically based on the properties of compounds, and there are 4 criteria that are used for these pi systems that need to be achieved in order for special aromatic stabilization to be observed. So we are going to look at some of the properties or the basic rules that have to be used in order for this range of compounds and others that may be regarded as, of course, I've talked about the carbocations and the carbocations and the carbanions can be regarded as aromatic as well. So we are going to look at some of the examples, but first of all we have to determine some of these rules which have to be made in order for a compound or a molecule to be regarded as organic. So the first one is that this molecule has to be conjugated. Now, conjugated in this sense is that each atom must be either sp2 or sp hybridized. So as we talked about the overlapping of orbitals, I've mentioned about the pi and the sigma bonds. The concept of hybridization comes from that sense. So therefore, the first condition for a molecule to be regarded as organic, it has to be conjugated. in a sense means that each atom must be either sp2 or sp hybridized. So condition number 2 is that they should be cyclic. So this one rules out the concept of aliphatic compounds, that is maybe branched chains, chiral, being aromatic. So therefore, when we talk about aromatic compounds being cyclic, this means that the linear systems are not aromatic. So therefore, as I mentioned, the chiral, branched, and even the long chain or the chain series of other compounds cannot be aromatic. Therefore, the linear systems are not aromatic. And then we have condition number 3 is that they should be planar. They should be planar. This comes from the concept of the word from basic geometry, the plane. And this is, of course, a two-dimensional space that runs indefinitely on 4 directions. So this is what we call a concept of a plane. Of course, the restrictions here are just for demonstration purposes, but a plane is a two-dimensional space that runs indefinitely in 4 directions. So we have a planar. The structure has to be a planar, and that ensures there is a good overlap for the interaction between the orbitals, which gives, of course, this concept of stability. So the essence of being planar for the overlap. This is for the overlap or interaction between 2 orbitals. There should be a good overlap or interaction between the orbitals. And the last condition for that is that they should observe the Haeckel rule. This molecule that has to be regarded as aromatic has to observe the Haeckel rule, which of course I'm just going to give in form of a formula. This is the number of electrons should be 4n plus 2 pi. Now we're going to see what basically entails n, and then we are going to see what basically by illustration this rule means. So these are the 4 basic rules for a compound or a molecule in order for it to be regarded as aromatic, which have to be met. So in summary form, the first one, it has to be conjugated, sp2 or sp hybridized. Number 2 is that it has to be cyclic. That basically means that the linear systems are not aromatic. 3, it should be planar. It's a good overlap of course, the good overlap for the interaction between the 2 orbitals, and then it should be observe the Haeckel rule. So I'm going to give the first illustration, of course, of the compound that I've basically been using as a representative of organic compounds, and that is benzene, in order for it to give us a clue of what these other organic compounds are going to observe. So I've given these ones. I'm going to show these hydrogens at this specific point. So in this case, this molecule of ours is known as benzene. We're trying to find out whether it is aromatic or not. So as we mentioned that the double bond is 2 electrons. So therefore, if the Haeckel rule is 4n plus 2 pi, this is going to give us 6 electrons. So therefore, for us, in order to find the value of that, we're going to have 4n equals 6 minus 2. And then we're going to have 4n is equals 4, therefore n is equals 1. So in this case, of course, when this is a number like that of course is going to be a whole number like that, then basically this confirms that the the benzene ring system obeys the Haeckel rule, and therefore it's an aromatic compound. So let's try to look at another example. I said that an aromatic compound from the definition is a compound that forms, or basically it's like benzene and a similar ring system. Now we're going to see a similar ring system that is, of course, compounded with another one, and try to see whether it is aromatic or not. So we have this compound here, and I'll use so in this case we are going to see that the number of double bonds in this particular system is 1, 2, 3, 4, 5. So 5 double bonds, and we have said that a double bond consists of 2 electrons. So we shall have a total of 2 times 5, which is 10 electrons. So for us to observe whether it obeys the Haeckel rule, we shall have 4n plus 2 pi equals 10. 4n is equals 10 minus 2. 4n equals 8 over 4 over 4. N is equals 2. So therefore this one obeys Haeckel's rule, and therefore it's an aromatic compound. Now I had mentioned that aromaticity is not restricted to, of course, the ring systems that we talked about, or the 6-membered ring systems, or just hydrocarbons or substituted benzenes. It can as well be observed by the carbocations and the carbanions, and which of course display the basic characteristics of aromatic compounds. And we're going to see some of the examples that we can be able to use to illustrate that these carbanions and carbocations display the concepts of aromaticity. Now I'm going to do 2 illustrations for this. Now basically the illustration that I've given, of course we have talked about carbocations and carbanions. This carbocation can be able to form a resonance structure like the second one that I've given. Of course we can see whether it is going to achieve the concept of aromaticity by trying to apply the Haeckel's rule, which of course we have mentioned as the number of electrons to be this one. So for this case, this one consists of a single of course double bond, which of course we have shown that it can be resonating within that space, and then we can be able to achieve that. So for that case we have 2 electrons for that double bond, and we'll try to see whether it obeys the Haeckel's rule, which is 4n is equals 2 minus 2, therefore n is equals to 0. And this is the only system where n is equals, of course this is the only system that we have done try to confirm the Haeckel's rule that is aromatic. For this the carbocations and carbanions that we have mentioned in one of the previous discussion for this kind of a topic. So what of some compounds which may basically be not be benzene or substituted benzene that we talked about? Can they be able to form aromatic compounds? I'm also going to give a subsequent illustration for that. I've said about carbocation, maybe we can give an example of a carbanion in order to confirm whether that species also the molecule obeys the Haeckel's rule, and other set of rules that we have mentioned, and therefore conclude whether it is aromatic or not. So the one I've drawn on the board is basically what we refer to as an ion. We had looked at the cation, and we confirmed that it can display the concept of aromaticity. So in this case, as we can see from the structure of this, there's a negative charge at that particular point. And if we try to find the structure, I'll try to see the resonance for that one. Can move there, and then this one can move to this point, and we're going to have this negative charge there, and therefore it moves, and then we shall have that double bond moving to this point, and then we shall have a negative charge here. and that one. So therefore, and this, of course, is the illustration. This is the basic illustration for the cyclodiene. This is a cyclodiene anion that we're going to use in order to confirm whether it obeys the Hackers rule and other conditions for it to be regarded as either aromatic or not. So we can see that there's the number of the bonds, the electrons that we have been using to illustrate for the double bonds there is 6. So we are going to have 4 pi, so 4n plus 2 pi equals 6. Therefore, we have 4n is equals 6 minus 2, which is 4. N is equals 4, implying n is equals 1. Therefore, we can say that this compound is aromatic. So in that case, there are other larger molecules which we can be able to use to illustrate the same, whether compound is aromatic or not. And now the opposite of compounds that, of course, the opposite of this of compounds which do not obey the rules that we have specified, and what we call anti-aromatic compounds, whereby the number of electrons or the electrons do not obey the Hackers rule. So these are anti-aromatic compounds, and maybe we just want to use an example. Now for aromatic compounds, a class of anilines and others that fall under this category, which are able to obey the set of conditions that we have given, can as well be regarded as aromatic, so long as the number of pi electrons observe the Hackers rule for either the benzene substituted, benzene unsubstituted, benzene substituted, and then the cyclic compounds. This one can be regarded as aromatic. So for aromatic compounds, we're going to give an example for this. So let's try to look at an illustration for one of the molecules that can be able to be used for this, for anti-aromatic compounds. So the illustration I've given is for a compound that is known, or a molecule that is known as heptadene. And this compound, of course, is planar and meets one of the conditions that we are given for organic compounds. But we're going to see that when we are trying to observe the Hackers rule, it's going to have 4n plus 2 pi electrons, which is going to be 1, 2, 3, 4, 5, 6 times 2, that is 12. So when we try to solve for n, 12 minus 2, this is 4n is equals 10. So n is equals 10 over 4, which is of course a fraction, which is 5 over 2. Therefore, this one does not obey the rules that we have mentioned. Therefore, this compound can be regarded as anti-aromatic. And if we give a second example of a compound, which we said that for a compound to be regarded as aromatic, it has got to be conjugated, whereby each atom must be either sp2 or sp hybridized. Let's try to look at this compound, which of course can be illustrated as such. So we have this compound. We're going to confirm that this compound is not conjugated. This is implying that each atom is not either sp hybridized or sp2 hybridized. Therefore, this is not going to be aromatic and can be regarded as an anti-aromatic compound. So basically, we are going to meet different examples of compounds that we're going to regard as aromatic or anti-aromatic. So in case we come across one, we'll be using this reference to this video as a concept for this kind of a conditional special condition that we have regarded as aromaticity or anti-aromaticity. So that is it for today, guys. Thank you. I hope that we have gained some of the concepts from this and we're going to use them appropriately. So bye. God bless you.